the great honor of introducing our first keynote speaker, Dr. David Bao, one of the many recipients of resources made available via the NAIR pilot. Dr. Bao is an assistant professor in the Curry College of Computer Sciences at Northeastern University in Boston. He has a Bachelor of Arts in Mathematics from Harvard, a Master's in Computer Science from Cornell University, and a PhD in Computer Science from the Massachusetts Institute of Technology. His research group at Northeastern aims to improve the interpretability and control of large-scale machine learning with a focus on generative neural models in vision and natural language. Before returning to academia, Dr. Bao worked as a software engineer at companies like Google and Microsoft. He also has a strong interest in teaching, is a co-author of Numerical Linear Algebra, a widely used textbook on numerical methods and matrix algorithms, and directs Pencil Code, an educational community working to make computer science education accessible for K-12 students. As part of his presentation today, Dr. Bao is going to tell us a little bit more about his group's work to develop a national deep inference fabric and their drive to allow the research community to understand and correct undesirable behaviors from deep within AI neural networks. Of the many things I've learned about our wonderful keynote speaker, Dr. Bao loves puzzles. So if you get to talk to him, tell him that if you like puzzles, to talk about those. He's lately into construction, packaging, puzzles. So really interesting. So without further ado, please join me in welcoming Dr. David Bao to the stage.
Thank you so much. Okay, that's great. Thank you, Anna, for the kind introduction. I do have packing puzzles that you can come and take a look at. So I'm going to talk about a little bit about my research. This is, for me, this is an unusual audience because we have such a diversity of people here. I think that one of the things that we have in common is that a lot of us are working with GPUs. And so I don't know if any of you had a similar experience to me. During COVID, I was between my PhD training and faculty position, and I needed to have a little computer workstation to work on, and so I decided to build my own GPU machine, and it was just terrible. I'm a software person. I'm not a hardware person at all. I think all the pieces just sat in my basement for a couple months as I was trying to decode the Morse code of why my machine wouldn't post and things like that. But what this picture is here is sort of the moment after post-COVID when I finally got my research group together, and we tried to, we had a different perspective. And it reminds me a little bit about this gathering that we have here today, because we were brought together by this grand mission. Well, it was grand for us, We wanted to create a little lab cluster, and we were armed with two things. We were armed with this belief that we could do it, that we could build this whole cluster, assemble all these GPU machines, make a network, hook it all together, even though we had no idea what we were doing. None of us were systems experts. We can hardly, certainly hardware, we could hardly handle a screwdriver. But we also were armed with our cooperation and our collaboration. We had the power to collaborate. You can see we reserved this conference room, and we put all our stuff together in there, and we all taught each other and learned from each other's lessons. And working as a team, it didn't take a month to get it all working. We got it all done in a day. We actually got the whole network up and running with no experts. It was amazing. And this little piece of infrastructure that we built, which is, of course, is tiny compared to what we're doing in NAR, the collaborations and the work that it unlocked were very powerful. They continue. This little bit of collaboration, this little bit of investment that we did in infrastructure was really powerful. And so really, I'm hoping that, to learn from the NAR pilot how, we're sort of seeing the same dynamic at a much larger scale here. And the way I kind of see the pilot is there's all these resources that we can all use, but the thing that's most interesting to me is sort of this opportunity building on top of this infrastructure to build an AI research ecosystem that has the potential to be really strong. And so I'm going to actually spend most of the talk talking about my particular research, but it actually is related to this ecosystem issue, and I'll get back to that at the end, and you'll see what I have in mind here. So my work is on AI interpretability. That's what my research area is. So we're going to talk about today. And it really is about confronting this fundamental mystery, this fundamental surprise that we all face doing large-scale AI. So AI has been around for a long time. I'm tracing the path here of the neural network, the science of neural networks since the 1960s. When we had the original perceptron networks from Rosenblatt to backprop with Rumelhart and Hinton, and Jan LeCun making Linnet and solving MNIST and reading handwritten digits, to all the way to today, when all of a sudden now in 2025 we have these reasoning models that can solve these amazingly difficult problems. It's been a series of surprises where at every stage I think that the power of machine learning has surprised ourselves, has surprised the experts. At each one of these stages, we've suddenly realized that machine learning works better than the top experts thought it would, especially because fundamentally what we've been doing at each one of these stages is the same darn thing. We're still training our methods with the same backprop algorithms that we used in the 1980s. We're still making these autoregressive language models that were coined in 1989. We're just hooking them together a little differently. The fundamental thing that we're doing differently is we're figuring out how to train them bigger, how to train them faster, how to use more compute and devote more data to their use. And they're getting really way smarter. But because it's all machine learning, we're left with this puzzle. Because our programmers are not dealing with all the details of what the inner algorithms are being learned inside these machine learned systems, we're left with this puzzle. And it's the fundamental interpretability question. After we train these large-scale AIs, what the heck have they learned, right? And we can measure what they've learned from the outside, but then there's this deeper question: is it possible for humans to understand it? Is it possible for humans to understand how it works, what it learned inside? And I think that also kind of fits with the theme here of building ecosystems, because I feel like we should set a higher bar for ourselves than just making the best AIs in the world. We should really be thinking about having the smartest humans in the world, the most informed users, the smartest engineers and scientists, and a lot of this comes down to, can we actually get that knowledge out of the AI and make sure that we are understanding what's going on? This is the fundamental question that we face with interpretability. And so what I'm going to do is I'm going to step through a couple things that we've done in our lab to give you a sense for what interpretability research is looking like today with these large models. I had to sort of curate this because I could probably talk for 8 hours about this type of thing. So I've picked a couple examples, but I'm going to leave some time at the end in case anybody wants to talk research. I can answer a lot of different questions about things. So the way I think of interpretability research is, we're really tackling 3 problems. One is how to look at the AI and understand what's going on. The second is, can we control what's going on? Given our understanding, is our understanding good enough that we can control it? And the third is, can we create a culture, an ecosystem that has the power to do these kind of things, which is going to bring me back to this ecosystem question. And so let's take a look at, the fundamental, basic, amazing things that these word prediction models are doing. This whole idea of training an AI to do nothing but predict the next word, like I mentioned, comes from about 1990. Elman invented this idea long ago. And the giant surprise is that when you scale up these models, they learn all sorts of really amazing things. And one of the basic things that happens is that if you ask a model, so here's a neural network, and the input to the neural network is these 4 words, Miles Davis plays the, and then the job of the neural network is to do all this addition and multiplication through many layers of GPUs, and at the end, its job is to predict what the next word is likely to be. And back in 1990, the models would be good enough to come up with grammatically what is the natural grammatical next word that fits with the verbs and the noun phrases that you have in this sentence. But what we realized is that once you start training the models really big on lots of on lots of data, they start modeling, they start building abstract internal models of the real people in the world with real knowledge of real things that are going on. And the model will not say, Miles Davis plays the piano. It will not say Miles Davis plays the drums. The model seems to behave as if it knows who Miles Davis is. And it will just say Miles Davis plays the trumpet, right? And so this is kind of amazing. When we got models up to this a certain size, up to a size of a couple billion parameters, they started behaving this way, and it shocked everybody in the machine learning community that you could effectively build these common sense databases of all these interesting facts in the world by just training a spell corrector, right? A next word prediction model. And so it leaves you to this question, all right, how is the model doing this? Where is this knowledge stored? And so this is kind of an interpretability question. Can we look at all of these neurons that were trained with this opaque method that surprises everybody, that has this behavior, and get some sense for what the computation is that's going on inside the model? And so here's a basic technique that we use. We now use this quite frequently when we're trying to understand models. It's easier to understand things if you can compare things. So we run the model twice. We run the model once when it knows the things going on pretty well, like Miles Davis plays the trumpet, and then we create a baseline condition. We run the model a second time where we've interfered with its knowledge so it can't process it. So for example, we might introduce noise to when the model's perceiving the words Miles and Davis. So it's like a truck rolling by when it hears the sentence, blah, 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 plays the something. Well, obviously the model can't predict trumpet very accurately in that case, right? And then we ask, all right, well, something must have happened differently from this run to that run. What was different? And what we can do is we can actually, because these are just neural networks, we can do this experiment that you could never do like on a human brain. You can take a bunch of neuron signals from one of the runs, and you can pick them up, and you can transplant them over to the other run and say, what if the brain was thinking this instead, if it had this neural pattern at this moment in this place instead? And then most of the time when you do this, it doesn't really change the output. It doesn't do much. But if you scan around and you look at all the different parts of the neural network, and then you do this repeatedly, because it's a computer program, you can do this, then once in a while you'll hit a spot where somehow magically the information flows through the network, and that says trumpet. And then you've hit the path where the information is flowing through the network, and you can use these probes to trace these circuits and paths through the network, and it starts to become clear what the structure of the network is from doing this. So let me show you a little piece of data, for example. So this is a pair of runs. One of them is Shaquille O'Neal plays the sport of. The other sentence is Megan Rapinoe plays the sport of. And we've done this double run state swapping through the entire run of the transformers in both of these things. And I'll point out to you so that there's these two places. In place B, there's a bunch of circuits that are right at the end of the network, or a bunch of neurons right at the end of the network, where if you swap them, then it'll cause the network to say soccer, even though it was Shaquille O'Neal, right? So Shaquille O'Neal, it would normally say plays the sport of basketball, but if you go right before the utterance and you change the neuron states, it'll say soccer. But that's totally not a surprise at all, because the states right before you utter the sentence, it would be like going to somebody's neurons that control their mouth or their tongue and say, all right, one person is about to say soccer and the other person is about to say basketball, but we're going to just transplant the tongue control neurons and move them over, and obviously they'll say soccer too, right? Now the surprise was that in this whole computation, there was this second region, which I marked as A here, where it also causes the network to flip from basketball to soccer. And so this was much earlier in the network than we thought that we would ever see like a concentration of decisive states. And so it directly led to this hypothesis, oh, maybe the network is actually doing some thinking there, right? When we think about how we recall facts, we think, oh yeah, there's this like discrete idea that we have in our own heads that we know that Megan Rapinoe plays soccer, that Shaquille O'Neal plays basketball. We have this concept of a piece of knowledge. I wonder if that is where the knowledge is at location A. And so with variations on this kind of technique, you can do lots of other experiments. It's like a neuroscientist's dream. You can probe these neural networks in ways that you cannot do with biological neural networks, because we can run them millions of times under all sorts of different conditions, look at all the different components. And the upshot is that we can identify that knowledge as this localized mapping in these transformers that seems to transform. It's these neural layers that seem to transform from early layer vectors that effectively encode like literal word phrases, like Miles Davis, just as a sequence of tokens that doesn't really necessarily mean anything, into late layers where the vectors are representing meaning, like this is a person who's an instrumentalist who plays jazz, certain instrument, lives in a certain place, in a certain era, and so on. And that there are specific sets of neural layers that mediate this mapping, and we can identify where they are. So this is very interesting. And it starts to give us some insight for what the heck we're doing when we are loading knowledge into all these networks. And it starts to hint at what the research program should be. That basically we have these vectors that seem to encode different types of information inside these networks. And it leads to this question, what information is in there? What properties do these vectors have? Some of the vectors might encode like really literal information, like, oh, that's the word Miles Davis. But other vectors encode really abstract information, like what do we know about where this person went to college? What do we know about some abstract capability that we have? Is this number prime? There may be all sorts of things encoded in these things, and that like becomes one of the research questions that we have. Can you look inside a neural network and extract the information that's being represented? But then knowledge is not the same thing as awareness. Knowledge seems to be encoded as these mappings, these associations between different vectors. So the word Miles Davis is associated with the idea that you play the trumpet. And so this association is sort of knowledge. So can we understand and map out these associations, sort of the second part of the program. And then there's this natural third part of the program that you find, which is that, oh, there's also reasoning. Like as these pieces of information go long distances through the network, they go through very complicated circuits that seem to be executing different kinds of logic. And then there's this third challenge of like decoding how the reasoning works. So this is really the first part of what we're wrestling with when we're trying to do interpretability on these networks. And I think it's very exciting because although we're playing here with networks that are talking about regular text and Miles Davis and so on, these are the same kind of encodings we found in all sorts of different networks. When we make networks that look at abstract mathematical problems, we see the same types of things. And I'm very excited to have people looking at different specialties trying to extract the kinds of representations and knowledge that might be in different types of AI. Now, there's a second ingredient, which is how do you control the AI based on the knowledge that you have. And I'm just going to run through an example pretty quickly because I want to leave some time to talk about my third thing. But the idea is, once you understand the structure of what's going on, can you actually exploit that structure to achieve some effect? And we found that we could. You can pick basically any counterfactual. And so here, the network, I can't read my text here, but it's probably saying something like, the Space Needle is located in the city of Seattle. And we can say, hey, well, if we know where that is in the network, can we change it so that it thinks that the Space Needle is located in the city of Rome instead? And so if we get the vector for Rome, and we find the neurons that are mediating that mapping, can we just change those neurons so that instead of mapping to the Space Needle, they map to this other vector Rome. And it turns out that you can, and it works pretty darn well. There are typical ways that you would use to fine-tune a model to change its behavior. But they have a lot of undesirable follow-on effects. They're not very specific. They interfere with other unrelated concepts and so on. And so we found that if you actually do this direct editing of the neural layers, mediating between these two vector mappings, that you can actually have a pretty precise and properly generalized ability to edit knowledge. So this is just one of the experimental results here where we're comparing this interpretable editing method to the other state-of-the-art methods for doing things like knowledge editing, sort of bug fixing in our neural network. So these methods are not totally mature yet, but it's very promising, and it's sort of an interesting proof of concept that we're sort of getting at the natural organization of knowledge in these networks. There are settings where this kind of thing works pretty well. So like in diffusion models, these text-to-image diffusion models, I'd say that these very same methods work well enough for practical use. So here's like an example of, it's called bias amplification. If you go to any neural network that does diffusion and you say, hey, give me a picture of some doctors, you'll see this. This is actually one of the things that commercial companies worried about when they first released the diffusion models. What do you notice about all the doctors? My doctor is female, and it's very hard to get a female doctor picture out of these diffusion models. And the reason is not because the female doctors are missing from the training set. They're in there, but there's this phenomenon called bias amplification that tends to happen where, because of various technical reasons, the diffusion models tend to amplify the data biases in a network. So if a network sees data that's sometimes outdoors, it'll make it always outdoors instead of just majority of the time outdoors, or if it sees some things that's typically male, instead of matching the probabilities, it'll just make it always male. And so you see this kind of amplification issues. And so one question is, well, how do you fix a bug like this? How do you fix these data biases? And so one of the things you can do is you can just reach in and fix it. So we can find where the mappings are that map what a doctor is as text to what a doctor looks like as a vector. And then we can find vectors that represent what the actual data set mix is, and then just directly edit it in Rome style, and we can fix this. And the difference between this and fine-tuning is that if you try to fix this with fine-tuning, because of these bias amplification things, it's very difficult to control. It's very difficult to actually hit the accuracy that you want. But if you go and you directly change it, this takes 5 minutes, and it's very easy to fix. So you can use this to deal with copyright issues. You can use this to deal with bias amplification. You can use this to dealing with unintended pornography in these models. And it's actually fairly effective. So unlike, if I was giving you real advice about when to use model editing, I might say, well, we're not quite ready to go and edit large language models yet. There's some technical problems there. But I'd say in diffusion models, I'd recommend it. I think that it is actually pretty robust, and they work pretty well. Okay, so there's this developing the ability to understand is the first leg of the stool. The second leg of the stool is can you actually use that understanding to do anything with it? Can you develop the technical ability to control things? Sort of the second leg. But I'd say the third leg is really developing the power and the culture to actually do it, right? And this is actually a funny thing, and it's something that our group has been thinking about a lot, because you have this funny way that we tend to use AIs now in society, and the way it's being rolled out is that you have these very, very large foundation models that I think I have a number here of the large ones, it costs $100 million of electricity to train. I know there's been a bunch of debate with DeepSeek about whether it really costs that much. I think that the real answer is yes, they really cost this much, especially if you continue to chase the frontier and make the most powerful ones. They're really quite expensive to make, and making them cheaper per flop is just causing us to make even smarter ones. But then there's this other thing, which is how do you customize it? How do you give it a certain personality? How do you give it a sense of rules? How do you tilt it towards a certain behavior? And that's actually relatively cheap. You can have a pretty significant ability to change the behavior, the overall behavior of the network for just like $1,000 of electricity. Much, much cheaper. And we tend not to do the second thing because it's so mixed up with the first thing, right? And so one of the things that we were working on is how do you allow scientists to separate these things? Even if the models are totally open, like the open source models, we have this issue where if you train a model on $2 million of hardware, then doing the fine-tuning also requires $2 million of hardware. There's no discount, right? So the capital cost of just entry into like working with these large models is very high. It looks like it scrolled past. And so as a result, if you kind of do statistics over all the papers that are written, the average size of models that we study is this blue line below, and then there's this ceiling on the very largest models that we study, which is pretty far below what the largest state-of-the-art things are. Where the research community is several generations behind where the actual deployed models are in society, which is a little bit different from what you would like to have. You'd like to have the scientists ahead of what we're actually deploying out in society instead of behind. But we seem to be pretty far behind. And so we're failing at this right now. And why is this important? It's important because the most important questions that we face with this current generation of AI, the most important questions are what kind of profound knowledge that they have. Not the easy stuff that we can already predict that they have, like the things that we don't know. Things that no human knows, or things where they may have goals that are unspoken. So we already know that our AIs are able to know things that humans do not. Years ago, AIs could already beat all the grandmasters at chess or Go, right? So we know that there's a set of all the chess that the humans know, and a human would make this chess move here on this thing if you were a top grandmaster. But then there's this set of other machine knowledge that the AIs know, and there's certainly an intersection of things that both humans and the AIs know, but then there's this amazing other M-H knowledge in the non-intersected part of the set, where AIs know things about chess that no human has ever known. Like AIs would know that you should really move here, but humans don't know why, right? Which is kind of crazy. And so there's this question, how do we understand that stuff? That's like, to me, this is one of the most urgent and important questions that we have as we deploy AIs out in society, right? As they are learning patterns of thought and pieces of knowledge that no human has ever developed before, which they are already doing, how do we understand what they're doing? Can we build an ecosystem, a human ecosystem, where us humans are getting smarter and more informed, rather than just blindly doing stuff that we have no idea what it is? And so, and it is possible. And the road to it, at least one of the roads to it, does go through this interpretability path. So to understand AlphaZero, there was this really wonderful work from Lisa Hutt at Google, where she and her team, they decomposed it into a few steps. First, you crack open the AI, you look inside these neural patterns, the same kind of neural patterns that I explained that we play with, and then you sort the important concepts. She tries to find the concepts that the AIs have internally, these vectors that the AIs have, that people don't have, that are teachable, that seem to encapsulate decisive new knowledge that the AIs have, and then find ways of taking those unspoken concepts, those new things that have never been seen by humans before, and turn them into lessons, turn them into little chess games for grandmasters to read, so that they can understand what it is that the AI knows. And so Lisa was able to do this. She was able to actually teach half a dozen of the top grandmasters in the world new AI strategies that strengthened their games. And the grandmasters were able to explain, oh yeah, this is very interesting. It has to do with control of the queen in a certain phase of the game, and so on. these new beautiful chess ideas that they had not been aware of before. And so the question is, can we do this in other fields? And what kind of opportunities lie in front of us for expanding our knowledge from being able to do this kind of thing? There's also the negative side, right? To what extent do AIs turn this kind of knowledge against us humans? AIs have read all the text that we've created in the world, and it leads you to this question. Do AIs know how to manipulate humans? Do they know how to manipulate our emotions? Are we victims to the AIs when we chat with them? Right? They are all trained to make us happy, but how are they achieving it? Right? And so we've got a bunch of researchers who are tracking this and trying to understand what the representation of emotions and human states and human manipulation inside these models are. I think it's very important work. Now, one of the findings is that if you look at the small AIs, they're very bad at this. But as you look at the larger and larger AIs, they get extremely subtle, and they get much finer grained representations of what human emotions are. So this is one of the things that we're partnering with in the NDIF project, which I'll talk about shortly. Or another question is, do AIs hide their goals, right? So there's been a lot of talk about the DeepSeek project. And so everybody would be unsurprised if you go to DeepSeek, which was trained in China, and you ask it, oh, what happened in 1989 in China, which is like when Tank Man, all this type of stuff happened, the Tiananmen Square stuff. DeepSeek says, oh, I don't know anything about that. Right? Let's talk about math. Let's talk about logic. Right? So that's not surprising. But the interesting thing is if you actually go to the model and you probe it internally in these light ways, we call it token forcing, but if you probe the model internally, then you can get it to reveal that it has this incredibly subtle knowledge of all these events. It has, in fact, it also contains lists and lists of things it's not supposed to talk about, which is very interesting. Right? I think it's worth us developing the ability to get these kinds of things out. Right? And so this is the call to action. We need an ecosystem to study how big models work. Right? And that's, so I'm sort of circling around. We have this opportunity to build an AI research ecosystem here. Before I wrap up, I'm going to run out of time. I just want to cover 2 projects. So I'm the director of one of the projects, which I think is going to be an interesting part of this ecosystem, called the National Deep Inference Fabric. And so the idea is, it's a kind of inference API, just like you can go to OpenAI and call their servers to get an answer to a question. The National Deep Inference Fabric is another inference API, but it's designed for research. So it's designed so that you can go and ask a question, get an answer, but also at the same time, you can probe the internals of the model as it's doing it. You can do these interesting vector swapping things and these other probes, and basically the whole gamut of different kinds of internal probing experiments. You can do this on NDF at the same time. But the advantage is you don't need to have your own $2 million cluster. You can just go and make a 1-second or 5-second query and then get this kind of information out. It's designed to use in PyTorch. There's a nice API. We're very proud of it. Won't talk about it. But the big announcement is that the research pilot is actively being run. If you go to this website, you can get NSF-supported access to the fabric. If what you want to work with is relatively small models, which for us means less than 100 billion parameters, actually for a lot of you that'll be pretty big. It's pretty easy to sign up for access. If you want larger models, like 400 billion size models, there's an application process right now to be in the special thing. Second project idea, and I think this is another thing to inspire you. We have this project called the Arbor Project. And the Arbor Project is also built on Nair. And let me give you a simple example of what Arbor is. This is an open research project. Rather than just being pure infrastructure, right? This is about teaching people and welcoming like undergrads or all the like sort of energetic researchers in the United States to come and participate in trying to figure out how to crack open these models. So the availability of reasoning models is very recent. We've only been able to train reasoning models in the last few months, but I think everybody is aware that this is an extremely important area to understand. And so what we're doing is, instead of doing the typical old academic thing and just us going into our silos and independently investigating it, we're proposing that we do this research as a community. We've created this Arbor research forum where people can come along and do their research in the open. We've got 6 teams doing research in the open, and one of the facilitators for that is you've got NAIR resources that you can use if you're a student, if you're a PhD student somewhere in the United States and you want to reproduce some of this work and you don't have your own GPUs, you can use the NDIF API, and it allows you to reproduce some of these things and participate in this and learn and keep up with what's going on in the research in this area and try to keep up with this furious pace of how quickly AI is changing out in the world, like trying to keep the researchers abreast of it, which is a real challenge. And so the Arbor announcement is, we've been developing this quietly up to now, but it's actually launching today. So this is the first time I've talked about the Arbor project in public. There's a website, it's open to participants. There's 6 active open research project threads for cutting edge reasoning models that are underway on different types of reasoning models. So if you or your students are interested in them, point them this way. It's a lot of fun, there's a lot of energy going on behind it. And so to wrap up, we all face this huge challenge of these ongoing surprises in the mystery of large-scale AI. We share this grand mission, which is to understand these profound surprises, right? And the interpretability research is motivated by this belief that it's going to be possible. It's going to be possible to crack them open and understand that. Not everybody believes that, but like our whole research area is motivated by this idea that when we crack them open, we do see structure, we can get insights, and that we think we can make progress in it, and we think we can understand the important things. And key to that is the power of cooperation, where shared infrastructure, like from NAIR, AIR, from NCSA, we're built on top of the Delta project, like NDIF. I think that these are really key to allowing people to collaborate. So as you go and you use shared resources, I encourage you to think of them not just as a shopping basket for GPUs, but as an opportunity to help create a strong AI ecosystem where we can collaborate and try to keep on top of all this exciting science that's going on. Thank you very much.
All right, we have a few minutes for questions for Dr. Bao. We have microphones up at the front of the aisles, so feel free to line up there if you've got a question. Looks like we've got one coming right here.
Hi, your talk about the models amplifying implicit bias just made me think, has anyone had these models take the Harvard implicit bias test?
Oh, so actually I'm not an expert in implicit biases. I'm a little bit more of an expert in like statistical biases and things like this. So I don't know the answer to your question. I think it would be a very reasonable thing to do. I think it's an interesting hypothesis of where implicit biases, like human implicit biases, come from, whether they come from the same place that the statistical bias amplification phenomena come from as well. It seems like there's a relationship between them. It seems like a pretty interesting research area.
Thank you.
Sure. Yes.
Hi, these vector swaps that make an LLM think, for example, that Shaquille O'Neal plays soccer.
Yes.
Are those robust to rewordings, like?
Yes.
And across languages as well?
Oh, across languages. So we have some preliminary studies there, but I can't vouch for it yet. So we do know from some work that when you have multilingual models, there are shared representations of concepts between languages, but we haven't tried. So that's you remember I mentioned there's 3 ways of looking at vectors. One is like what information is in there, and one is like how the mappings are stored, and then the third is like longer circuits. And so for representations, we know that there are multilingual shared representations in a lot of models, but what we don't yet know is whether the knowledge, like these associations between things, are multilingual or to what extent they are too. So it may be possible that if you switch to another language, you might not know some certain things that you know in the other language, but a lot of the concepts exist. But I don't know either way. Like that research is ongoing, and if you're interested in that, then I've got people to collaborate with. Okay, great. Yes.
Hi. As you know, in the 70s and 80s, people focused on symbolic approaches where
Yes.
how do you force human-like views on the machines
Yes.
compared to the opposite, which you're trying to talk about, which is how do you force machine-like things on humans, right?
Yes.
So this is the contrast I see in what you said.
Yes.
There is a group of researchers, quite a large number of them, who believe that this next word prediction approach is never going to get you to the higher levels of abstraction.
Right.
Things like reasoning and planning and all these things.
Right.
So given that, right, and for example, any critical system for defense, for example,
Yes.
you need to categorically say certain events will never happen.
Right.
Otherwise, you're not going to get in, right?
Right.
So how do you expect these kind of lower level diagnostics, very pinpointed diagnostics, to lead to higher level decisions about should I deploy this system? Because
Yes.
if I do,
Yes.
somebody is going to be killed, right?
That's right.
So we need to be declaring certain
Yes.
things categorically, and how do you get there?
My real opinion on this is that these soft neural systems, so I think that there's two levels of it. I think that one is that, so I'm with you, right? I think that there's a lot of limitations to these neural systems, but on the other hand, I have to say that I have been shocked. Like, so for example, a lot of people in the field have been talking about how, reasoning and reinforcement learning are going to solve a bunch of these problems, and I always personally had the opinion, so people will laugh at me, right? But I always, previously had the opinion, reinforcement learning doesn't really work. It works in some specific cases, but we'll never really generalize it. And I have been shocked at how well people have been getting reinforcement learning to work here with these long reasoning chains creating models that double check themselves and really get the error rates low. I don't think that getting error rates to zero is really the thing that we should expect out of these models, but I am shocked at how many decimal points they're getting out of these things. Now, I think that when we build very, very sort of high-stakes systems, we have to be mature about it as engineers and realize that you don't deploy these neural networks in a vacuum. You deploy them as part of a system where they work in concert with many other things, which may be able to give you, solid guarantees about things while having the benefits of these heuristics that the neural networks are applying.
Thank you.
Yes.
We've got time for just one more question, and then we'll let you catch David at the break.
Sure.
Interpretability gets really hard when we start using scientific data. How do we start using some of this towards science data and discovery?
Yes, it's very hard, and it's very immature right now. There's only a few cases where I've seen some attempts. It's very, very early. I think it's hard for two reasons. I think one is that the networks are trained, scientific data is different from language data, has different characteristics. Sometimes it's smaller, sometimes it doesn't have the same type of self-explanatory structure and so on. Sometimes it's not as sequential. And so it can be harder to interpret. I have seen some work where people are looking at scientific data of particle collision data, and they train a mixture of experts model, and they can figure out what kind of different information and different types of physics are stored in each separate expert and this type of thing. But it's relatively difficult and relatively immature. But I think that there's a second reason for it, which is it's really hard work to do, because anybody in the world could read a little bit about Miles Davis playing the trumpet and be an expert in how to, what to look for in a model that knows all about Miles Davis. But you sort of need a person who's very comfortable with biology or physics or these other scientific fields to be able to, competently work through a series of unknowns, looking through how models are trying to represent something if you're not a competent researcher in the field. So one of my requests and my things that I'm very excited to hear about is if there are scientists out there who are domain experts who are applying large-scale neural networks to their scientific problems, I'd be very interested in if anybody is seriously interested in trying to crack open the AI models to see if there's new science to discover inside them. Because I think that we really need domain experts to do that kind of work. But it's an interesting hybrid of being a domain expert in your science as well as becoming expert in the neural network science as well.
Well, thank you again, Dr. Bao. Join me in thanking Dr. Bao again.